Hello everyone, this is Professor Roman. Welcome to the 34th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to talk about the Stirling numbers of the first kind. And in order to do this effectively, we first need to make some comments about permutations. And for convenience, I'm going to assume for this discussion that the underlying set is the set zk, so that's the integers from 1 to k. But it could be any set of size k, it doesn't matter, but this will be the most convenient one to use. Now, as we've defined permutations, we did it in a combinatorial way. A permutation is just an ordered arrangement, in this case of the elements of zk. So here's an example of a permutation of zk. But permutations can also be thought of as bijections of the underlying set. So for example, this permutation would be written this way as a bijection. So the top row of this matrix is just the elements of the underlying set in order. And the second row is the elements in this ordered arrangement, also in order. And the map pi, the bijection pi, sends each element in the top row to the corresponding element directly below it. So pi of 1 is 4, pi of 2 is 6, pi of 3 is 1, and so on. And because the second row is just an ordered arrangement of the first row, this map is a bijection. It's surjective and it is injective. It's also clear that we can pass back and forth between the ordered arrangement view of permutations and the bijection view of permutations as functions, as bijections. So these two viewpoints define the same concept, just in a different language, from a different perspective. The support of a permutation, sigma, of zk, is the set of elements of zk that are moved by the permutation. So here it is in symbols. Support of sigma is the set of all elements x in zk, for which sigma applied to x is different from x. So x is moved by sigma. If sigma of x equals x, then we'd say x is fixed by sigma. So the support of this permutation is the set 1, 2, 3, 4, 5, 6, because all of those elements in the top row are moved. 1 is moved to 4, 2 is moved to 6, and so on. The only element that's not moved, that's fixed, is 7. So 7 is not part of the support of the permutation. Two permutations of the same underlying set are said to be disjoint if their supports are disjoint. Now, we come to a critical definition. A cycle of length m less than or equal to k, zk is our underlying set, also called an M cycle, is a special type of permutation, which I'm calling sigma, of zk, for which there is a subset of the underlying set, so z1 through zm, upon which sigma cycles through the elements of S and fixes all the other elements. So this, I think, will clarify that definition. Sigma sends Z1 to Z2, and then it sends Z2 to Z3, and so on until it reaches Zm, and then sigma sends it back to Z1. So it's a cyclic permutation. Z1 to Z2 to Z3 and so on to Zm back to Z1. Everything else in the underlying set that's not one of these elements Z1 through Zm is fixed. And it's customary to write a cycle in this form with parentheses and with spaces in between the elements. I think some authors use commas, which would be a good idea if the elements were complicated, had some algebraic symbols or something in it. So for example, as a permutation of Z7, this 4 cycle sends 1 to 6, 6 to 3, 3 to 2, and 2 to 1. 1 goes to 6, which goes to 3, which goes to 2, which wraps back around to 1. And what's missing from this cycle are 4, 5, and 7. They are fixed. As long as there are at least 2 elements in the cycle, as long as it's a 2 cycle or larger, the support are the elements in the cycle. So in this case, the support of pi here is 1, 6, 3, and 2. Those are the elements that are moved. When m is 1, when you have a cycle of length 1, well, Z1 then is sent to Z1. But everything else is fixed. So everything is fixed. Z1 is fixed and all the other elements are fixed. So this is the identity bijection. And its support is empty. Cycles are, in fact, the building blocks of permutations. And by that, I mean that every permutation can be written as a product, and by product I mean composition, of pairwise disjoint cycles. Pairwise disjoint means the supports are disjoint, pairwise disjoint. So let's look at an example that should clarify. Consider this permutation. Okay. This was the earlier thing. Yeah, it's the same one as this one up here, but that doesn't really matter. Okay, to see that this permutation is a product of cycles, in fact, pairwise disjoint cycles, start with any element, and 1 is as convenient as anything, and we repeatedly apply the permutation until we return to 1. So 1 goes to 4. These are the elements in red. 1 goes to 4, which goes to 5, which goes to 3, which goes back to 1. And so it's written this way. Okay. And that is this 4 cycle, 1, 4, 5, 3. Next, we pick an element of the underlying set, which in this case is Z7, that is not in the support of this cycle. So it's not 1, 4, 5, or 3. So we may as well pick 2, and we follow it by repeated applications of sigma. 2, these are in blue. 2 goes to 6, 6 goes to 2. So we get this little 2 cycle. You can start anywhere you want. You could start with 6. 6 goes to 2 and 2 goes to 6. So your 2 cycle would look like 6 followed by 2, but it's the same permutation, the same bijection. What's left after these two cycles is just the number 7, which goes to itself. So it generates a little 1 cycle, which is the identity, but we still include the 1 cycles. Now, since these cycles are mutually disjoint, an element of Z7 is moved only by the cycle in which it appears. So, for example, 6 is not moved by this cycle. By definition of a cycle, 6 is fixed. 7 is fixed. So when we take this composition, and that's usually called a product, and apply it to 6, this is the identity. It doesn't move 6. This one will move 6 to 2, and this one doesn't move 6. It fixes, 2. It doesn't move 2, so out comes 2. In goes 6, out comes 2. The only relevant portion of this composition is the cycle that contains 6. What happens to 5? Well, this doesn't move 5. This fixes 5, this fixes 5, this moves it to 3, so pi of 5 is 3. Okay. This is ordinary composition of, well, bijections in this case. But all the bijections except one don't move the element you're applying this to. This is called the cycle decomposition of the permutation. Okay. And if you think over this algorithm for producing the cycle decomposition, it is pretty clear that the cycle decomposition is unique. You could start, if you didn't start with 1, you could start with 7. You would get the 1 cycle first. If you started first with 6, you'd get this cycle first. You're going to get the same cycles no matter how you do this. Now, the only non-uniqueness to the cycle decomposition is the order of the cycles. Because they are pairwise disjoint, you can write them in any order. It's not going to make any difference. So the cycle decomposition of a permutation exists and is unique up to the order of the factors. And this argument that I just gave in the case of pi is pretty clearly going to work for any permutation. But if you're not satisfied with that, which is reasonable, and you want an actual proof, this is a perfect opportunity to illustrate the power of equivalence relations. So let's go through the argument. So pi is a permutation on zk. And I'm going to say that two elements of zk are connected. I maybe should have said connected by pi, if some power of pi applied to I is equal to j. So you can get from I to j by applying pi an appropriate number of times. Now, m is an integer. It could be positive or it could be negative, which is fine because pi is a bijection, so it's invertible. I'm going to leave it to you to show that this is reflexive, symmetric, and transitive, and is therefore an equivalence relation. Connectedness is an equivalence relation. Therefore, zk is partitioned by the equivalence classes. So the thing to do is figure out what the equivalence classes look like. Well, the equivalence class containing an element I in ZK consists of all, by definition, all the elements of ZK that are connected to I. So it's all these powers of pi applied to I. But we can simplify this quite a lot, because ZK is a finite set. When we start with I and repeatedly apply pi, sooner or later there's going to be duplicate entries, because this is potentially infinite, but there's only a finite k elements in ZK. So at some point, pi to the Ri is going to equal to pi to the Si, where we can assume R is less than S. So we apply pi to the negative R power to both sides of this, and we will get this, that pi to the power S minus R, it's a positive power, fixes I. So there's a smallest positive exponent, which I'm calling t, for which pi to the t fixes I. Now, looking back at this again, if we take an exponent m and we divide by t, we get qt plus the remainder. The remainder is a non-negative, but less than t, less than or equal to t minus 1. So pi to the mi is pi to the qt plus ri, which can be written this way. Well, pi to the t fixes I. So if you apply pi to the t q times, you're still going to have I. So this is pi to the ri. So R is in this range, and that tells us that the equivalence class containing I is just the elements I, pi I, up to pi to the t minus 1 I. That's a big improvement over, well, over this. Okay. What is this set, this equivalence class? It's the support of this cycle. So this cycle is part of the permutation pi. I is sent to pi I, which is sent to pi squared I, and so on. The point here, that's obvious, the point here is that pi to the t minus 1 I is sent back to I. If we apply pi again, we get pi to the t, and pi to the ti is I. Now, there's 2 points here. That's one of them. But the other one is that the equivalence classes of this relation, which is right connectedness, it partitions Z sub k, which means all of these cycles, their supports partition Z sub k, the underlying set. So pi is a product of these cycles. The product of these cycles contains all of the underlying set. Okay, so just quickly go back. Permutations can be thought of as bijections. The support of a permutation then is the set of elements that are moved under the bijection. A cycle is a particular type of permutation. It cycles through some elements in the underlying set, and everything else is fixed. And any permutation can be written as a product of pairwise disjoint cycles. It is called the cycle decomposition of a permutation, and it's unique up to the order of the cycles in the product. Okay. There's a parallel going on here. We've talked about partitions of a set before, and a partition of a set is a decomposition of the set into, generally speaking, smaller subsets. Here, and there are many ways to form a partition of a set. Here we have more structure. Permutations have more structure than just sets. The decomposition of a permutation into pieces, into cycles, always exists, but it's unique up to the order of the factors. That extra structure forces the uniqueness. But there's a parallelism there between partitions of a set and cyclic decompositions of a permutation. Well, now we can describe what the Stirling numbers of the first kind actually count. The Stirling numbers of the second kind, you will recall, capital S and K, count the number of partitions of a set of size n into k blocks. So you might be guessing now, the Stirling numbers of the first kind count the number of permutations of size n that have k cycles in their cycle decomposition. But there's a little wrinkle, nothing serious. Okay. In both cases, we are decomposing an object into simpler parts. This is an extremely common process in mathematics. You're faced with dealing with complicated objects, you want to decompose them into simpler objects. So by way of notation, I'm going to denote the set of all permutations of a set of size n, that'll typically be z sub n, but it doesn't have to be, whose cycle decomposition contains exactly k cycles by this perm n comma k. Then the size of this set, in other words, the number of permutations of size n whose cycle decomposition contains exactly k cycles, is denoted by little c n k and is called a signless Stirling number of the first kind. This number, where we're adjusting the sign by multiplying by -1 to the n minus k, is little snk, and that is a Stirling number of the first kind. This factor that we have to introduce here, the reason for it will become sort of apparent when we discuss some of the properties of the Stirling numbers. You'll see how nice they are. If you were to not include this sign correction, -1 to the n minus k, you'd have to include it in the formulas later, so it's simpler, I suppose, to include it now. But except for the algebraic sign, the Stirling numbers of the first kind count the number of permutations of size n that have exactly k cycles. Just like the Stirling numbers of the second kind count the number of partitions of a set of size n that have exactly k blocks. There's a perfect parallelism here. Now, there is an explicit formula for the Stirling numbers of the first kind, but you're not going to like it. It's derived from, and the explicit formula for the Stirling numbers of the second kind together with some other formulas that connect the two types of Stirling numbers that are getting more complicated than I want to get into in this introduction to Stirling numbers. But this is the formula. It's pretty ghastly. It's a double summation. As far as I know, there is no simpler formula. I don't believe that there is. Okay. So it's kind of unfortunate, I suppose, but someday maybe a simpler formula will be discovered. The fact that there is no, at least no known tractable formula for the Stirling numbers of the first kind makes the existence of a recurrence relation even more important, for computational purposes as well as theoretical purposes. Now, we can derive the recurrence relation using, again, the analog of the derivation we did for Stirling numbers of the second kind. You might want to go back and peek at that again, and you'll see that what we're doing, or what we're about to do, parallels what we did then. So we first observe that there are two ways to build permutations in this set perm n comma k. These are permutations of Zn that have exactly k cycles in their cycle decomposition. One way is to start with a permutation of size n minus 1 that has k minus 1 cycles and simply toss in one cycle containing what's missing from Zn minus 1, which is the integer n. So here's an example. This is a permutation of size 8, a permutation of Z8 that has 4 cycles. And I just adjoin or append a one-element cycle with the element 9. So here it is at the end. And this is now a permutation of Z9 with 5 cycles. Now there are Cn minus 1, k minus 1 permutations in this set, by definition of the signless Stirling numbers. And so this construction of appending a one cycle will produce Cn minus 1, k minus 1 distinct permutations in the set we're trying to count. But there's another way to produce permutations in this set, and that is we start with a permutation of Zn minus 1 with the full number of cycles, k, and we slip n somewhere in one of those cycles. Okay. So, for example, in this permutation here, in perm 8,4, we could slip a 9. Let's look at the first cycle. Where can we slip a 9 and get distinct permutations, distinct cycles? Well, we could put it before the 1. We now have a 4 cycle. We could put it between the 1 and the 6. This is a different 4 cycle. We can slip it between the 6 and the 4 and get yet another 4 cycle. If we try to put it at the end of the cycle, we get the same thing as if we put it at the beginning. Okay. This one does the same thing as this one. This goes 1, 6, 4, 9, and then back to 1. This does too. If you start with this 1, 6, 4, 9, back to 1. Okay. So in general, we can insert the missing integer n in front of any of the n minus 1 integers in the cycle decomposition of pi. in any of the cycles, but if you're going to put it in the front of the cycle, you can't put it at the end. So that's going to produce n minus 1 times this number permutations in the full set perm nk. Now you have to convince yourself of two things. The permutations you get here are distinct. These permutations are distinct by design. And none of these permutations can be the same as any of these, because these permutations don't have a one cycle containing n. All of these do, none of these do. So you're getting this many plus this many permutations in perm nk. Second, you have to convince yourself that that is all of perm nk. Every permutation of size n with k cycles comes in one of these two manners. And I'll let you think on that. In any case, when you add those two together, you get this nice recurrence. These are the initial conditions, and this is just by custom. So we have our Stirling numbers of the first kind. We have the signless version, which actually does the counting of the things we might be interested in. And we have an explicit formula, and we have a recurrence relation. And the explicit formula is pretty bad. If you remember, when we talked about the Stirling numbers of the second kind, we had some connection formulas. X to the k can be written in terms of lower factorials using the Stirling numbers of the second kind as coefficients. Well, we have an analogous thing here. In this case, it's the other way around. The lower factorials can be written as linear combinations of powers of x using the Stirling numbers of the first kind. That's why we want that negative 1 to the n minus k in the definition. If we put a CNK here, we'd have to stick the negative 1 to the n minus k in the summation. So it's 6 of one, half a dozen of the others, but it is convention to define the signless Stirling numbers of the first kind. As the proof here, if you remember, the proof of this that I gave was a combinatorial proof involving surjections rather than an algebraic proof. Well, here is the algebraic proof for this formula, and it's inductive. And I don't have the heart to go through all of this, so I'll let you read it for yourself if you want to struggle through it. In any case, we have both of these relations, and in combinatorics, these two sequences of coefficients would be known as connection constants because they connect these two polynomial sequences. That's big business in combinatorics, but even more so in the theory of special functions, which is something I would prefer not to go into. Okay, it can be somewhat unpleasant. A lot of equations, a lot of summations. Now, if we use the first equation in the second, if we replace this by all of this, it'll look like this. And I'm going to let you simplify to get to this point. So this very nice, handsome sum is the Kronecker delta NM. And you may know the Kronecker delta function, delta nm, is 1 if n equals m and 0 otherwise. So this is a handsome formula that describes what happens when you multiply the two types of Stirling numbers together and then take their sum. Well, that completes our discussion of both types of Stirling numbers. So now you know what they are, you know what they count. The takeaway here is that the Stirling numbers of the second kind count the number of partitions of a set of a given size into a given number of blocks. It's a decomposition. And the Stirling numbers of the first kind do something similar for permutations. They count the number of permutations of a given size that have a given number of cycles in their cycle decomposition. And then the rest is algebra. There are recurrence relations in both cases. There are explicit formulas in both cases. And there are connections between the two Stirling number types. I'm going to close with a little anecdote. Now you know what the Stirling numbers are. When I first started teaching at MIT, I met one of the senior professors there. We became friendly. We did some work together. And we were good friends for many, many years. And at that time, he was teaching a graduate course in combinatorics. And I'd only been doing combinatorics for a few years. I'd just gotten my PhD and got a position at MIT. And I thought it would be a good idea for me to sit in on his course. And much of the material I knew, but much of it I did not know. So it turned out to be very useful for me to sit in on his course. But there was a student. I sat in the back because I wasn't a student. There was a student. He sat in the front. And every day he would ask 4, 5, 6 questions, maybe more. And they seemed like very piercing, complex questions. And I was impressed by the fact that he seemed like he really knew the subject matter, and he was inquiring more deeply of my friend, the full professor, who always had a ready answer. One day, my friend and I were walking down the hall, and I said to him, what about this student who sits in the front row and asks all these questions? He seems pretty impressive. He seems like he's really following what's going on. And my friend said, he doesn't have a clue what's going on. In fact, he doesn't even know what the Stirling numbers are. So that's my anecdote. You know what they are now. A graduate student at MIT did not know, taking a combinatorics class, did not know what they were. Okay, thank you for watching the video. Hang in there. I know this is a step up in complexity from what we've been doing. We've got a ways more to go here on this optional material. Hang in there if you can, and I'll see you in the next video.